Welcome to Physics Can Be Fun with me, Stephen Thomas. I am talking about teaching science in a revolutionary way. I am talking about what if we just didn't give a single note. We said come into class, we create a culture of science. The only thing you're going to walk out with is what you learned from watching and discovering and acting out what you see. So what is a culture of science? How can we create in our hour of teaching a culture of science? Now this is probably the most complicated little thing that I'm going to possibly use. It's a little boat. It's got a motor with a propeller on that side, and it's got a little PV or photovoltaic cell on the other side. And if we shine a light on the panel, it turns the motor. Is there anything that we could float it in here? And then maybe we could say, well, here I've got a little incandescent bulb. Let's see, I know sunlight turns it, but let's see if an incandescent bulb turns it. So we turn on the bulb, nothing. Let's bring it a bit closer. And so we see that when we bring the bulb close enough, the little motor turns. And then we could say, well, what have you learned from that? Well, they're learning the inverse square law. They're learning that there is a particular point at which the light seems to be strong enough around the bulb, but then it spreads out and weakens. So we could talk about the inverse square law, whereby the light dilutes itself by the square of the distance. Or what about as we float this boat in the water? Unfortunately, you can't see it. The boat doesn't sink. Newton 1. It's standing still. So we act out Newton 1 there. An object will remain at rest unless acted upon by an unbalanced force. So then we could go to a free body diagram of here is our little boat. And there's a force down, that's the weight of the boat, and there's the water. Something must be balancing that, and they're familiar with, so this is the force of weight or gravity. They're familiar with a force that's normal, and we say buoyancy is holding up the boat. So here we've got Newton 1. And then as the light shines on the boat, we could move on the little panel. We see the boat travels across our little pond. So now we see Newton 2. We represent Newton 2 by this, acceleration. So we could say when a boat starts from naught, there must be some force that's accelerating it. So there must be a force in that direction. And then the force causes the boat to accelerate. Because if you go from naught to a velocity, that means a change of velocity, which is acceleration. Then we could say, well, I wonder if all light works. So maybe if we used a different bulb, I'm going to take this bulb out, it's a bit hot. Ooh, we could talk about that. Look, feel how hot this bulb is. So obviously this bulb is losing a lot of energy and heat. This is an incandescent bulb. So we can get an LED bulb. Now we could discuss and see, let's see if that bulb works. Let's turn that around. Ooh, look how bright that is, everybody. Sure, surely something as bright as that, it's going to work fantastically. No, nothing. That's quite a weak bulb. No, nothing. And the kids could play it, but be careful. Electricity and water, don't mix. And there's the formula for the photoelectric effect, of which this is an example, where light falls on a metal panel. The light comes in little balls called photons, knocks the electron off. The electron goes through the motor because the electron's got a bit of kinetic energy left over. It comes back to the panel. So we saw that the incandescent bulb had enough oomph to knock the electrons off. The electrons had enough oomph to turn the propeller, and so on. And so we explain to them that the energy of the light comes in little balls called photons, and the photons just depend on two things: a constant, which doesn't change, Planck's constant, and the frequency of light. So it must be different frequencies of light being given off by an LED bulb, a fluorescent bulb, both of those don't work, and by an incandescent bulb. And it's the higher the frequency, the higher the energy. You could see they're directly proportional. Higher the frequency, higher the energy. Now there's a certain threshold frequency which has enough energy just to get the electron to leave the metal atom. Why don't we get the learners to act this out? So they're not sitting here writing notes, we're just getting them to act out. Right, class? Here, you're an electron, you're sitting on a metal atom. I give you the threshold frequency or work function, that's called amount of energy. All I want you to do is stand up. Okay, so I give you work function or threshold frequency, class. So you stand up. Now, what's going to happen if I give you more energy than work function or threshold frequency? Both of which are the same thing, except just differ by a constant. Okay, let's give you more energy, class. Now they've got to, you teach them, they've got to stand up and exhibit a bit of kinetic energy, get them to rotate around. Okay, now let's do it with a lower frequency, less energy than work function. So then you must tell them, okay, now they're just going to sit here, because they don't have enough energy to leave the atom, and they certainly don't have any kinetic energy left to go and do any spinning around. So now we've acted it out. They don't have it in a note. They don't have to come back at the end of the year and remember, what was it that we learned? The goal is to get this into long-term memory by playing with scientific stuff. We could also say, what about motors? Well, this is a little motor. Now, what does a motor consist of? We're going to act it out. Okay, so here's a little motor. Does it consist of magnets? Well, let's try and see. Oh, look, it's picking up some pins. So a motor contains magnets. Okay, class, there's you're a magnet. Got a north, a south. These are little field lines. They go from north to south, like this. Okay, so act it out. They're the field lines. Now, inside the motor is an armature or coil that turns. Act it out, class. They're going through the field lines like this. Right, and then we've got little split rings. That's the last thing. The split rings, if I had another hand, I'd put it there. Here's our split rings. And so those are the components that make up a motor. It's got its magnets, not very strong in this case, with the field lines. These are the fingers represent the field line. And then we've got an armature or coil that turns, and as it cuts the field lines, when it's horizontal, look, cutting the field lines, it creates a little spike in voltage. If this was a generator. So a motor and a generator are the same thing. Let's just pretend that this is a generator. And it is a generator. Motors and generators, same thing. So motors and generators, they both have got a magnet, they both have fields, they both have an armature or turns, but here's the difference. If I take a source of electricity and I apply it to my motor, you'll see that the motor turns. So that is a motor. What is energy? It depends on me giving it electrical energy. If I turn this, it's going to kick out energy. So we teach motors, and it becomes a generator. By me turning this, out will come electricity. If it's a motor, in comes electricity, out comes turning. In the one case, electrical energy comes in, mechanical energy goes out. In the case of a generator, mechanical energy, turning energy goes in, electrical energy comes out. So now let's act this out. Okay, so here's your armature, here's your field lines. As the armature turns, it becomes horizontal, it cuts the field lines, we get a spike. Then as it turns and becomes vertical, our generator goes back down. So let's move this out the way. And here is our voltage over time. of a DC generator. So then it's like this. Then as it turns again, now the armature is going to cut the field lines again, and so it generates another spike and another spike and so on. So now we get them to act out. Okay, now you're going to be the voltage. And here's the field lines are still there. Turn. Whew. Turn some more. Whew. Naught. Turn again. Now it's cutting again. Voltage up. Turn again. Voltage down. Turn. Voltage up. Turn. Voltage down. Turn. Voltage up. And so we create this thing called a DC wave. So now we can put it into a little song. My split rings makes me behave like a DC wave, like a DC wave, and they sing it. And then you could go and say, if this was a AC motor, this is what the graph would look like. This turns, the voltage goes up, maximum, same as a DC motor, down to 0. But here, as it turns again, now goes negative. So this is what a DC, this is what an AC generator looks like. And that is what we call a sine wave, folks. So the difference only is that in the case of an AC motor, instead of having these split rings, it's got 2 slip rings that go all the way around. 2 slip rings, and these 2 slip rings attached to our armature's coil. So now we have a little song for that too. We say, my slip rings make me behave like a sine wave, like a sine wave. And so we go both ways because it's alternating current. So there you see the current is going both, one way positive, then negative. And we could also get them to act it out. So there's the armature, right? Here's the field lines. What's the voltage? Naught. Now here it comes. Okay, so it rises to positive. Goes back to naught. Turns some more. Now in that position it goes negative voltage. Then it comes around again. And here it goes back to naught. Then positive voltage. Naught, negative voltage. And so by acting it out, the learners don't have to have a notebook full of stuff. They've got it up here. That is why it's so much more important now that we spend an hour creating a scientific culture of science and use that hour to get it actually into their memory. This is almost like the time before the exam. We want you to walk out with no notes, just go and walk out with the understanding of the concept. And look in the short term, we've covered Newton's laws, we've covered motors and generators, we've covered the photoelectric effect in just one lesson with one little toy, with a lot of fun science.